Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam Harris, a former mimicker turned mather.
And I'm Kim, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
This time I didn't say
I did it on purpose. Last week I wasn't paying attention to you.
We know that algorithms are amazing achievements, but they're not good teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we help you teach mathing.
Something somewhere.
Building relationships with your students and grappling with mathematical relationships.
Y'all, we invite you to join us to make math more figure-outable. All right, Kim.
Hi.
This one's starting out great. It's fantastic. This is going to be super, super fun.
Oh, man.
How's it going?
Yeah, we're good. Okay. You know what? Shelley Gilbert sent us a message.
Hey, Shelley.
And said, I've been listening to you and learning from you for a while now. I'm a retired public school teacher and now teach some math content and methods classes at the University of Findlay.
Ooh.
I pulled a book off my shelf that I used as a middle school teacher, and it was your Building Powerful Numeracy book. It took me all this time to make the connection. I've been using problem strings, as close as it gets, etc., for years. And when I stumbled onto the podcast, I thought it was wonderful to hear someone talk about these ideas. Isn't that great? I guess you talking about your ideas is not so unusual.
That's amazing. Awesome. Oh, that is so stinking fun.
She said, thank you for sharing your passion with math. You've made me a better teacher, and I hope a better preparer of future teachers. Kindly, Shelley. I love that. So
Shelley, you're amazing. You're exemplifying. Kim and I often are doing something, and all of a sudden we're like, oh, wait, duh. Sure.
Yep.
Well, I'm glad you've enjoyed Building Powerful Numeracy in your middle school class and as you teach teachers. Fantastic. Yeah, you're gonna also enjoy developing mathematical reasoning, avoiding the trap of algorithms, because
it's so good.
That's a bit more K-12. A bit more? It is. It's totally K-12.
Totally K-12.
And so, use that in your methods classes. Oh, in fact, any university folks out there know that you can totally give us a holler and we'll help set you up to use our Developing Mathematical Reasoning workshop in your methods classes. We've got lots of professors using it for assignments and asking questions about it. Totally free. We're just really trying to spread the word that math is figure-outable. Bam. All right, Kim, that was awesome. Thank you for sharing. That's super fun. Thanks, Shelley. So the last few weeks, we've been doing some solving equations and creating mental maps of relationships. We've been using double open number line. Last week, we really kind of talked about a way, and you had a lot of fun with that, a way of using a context to develop what a system of equations even is.
Yep.
And how you can add equations in a system and still get something that's in the system that has the same intersection point, and how you can kind of make sense of that.
Yeah.
Today, I'd like to dive into a little bit of a different side of systems of equations. And I want to develop something that that would be helpful for students in solving systems. So a first thing that we would need to do before we do what we do today, I'm just going to mention, we're not actually going to do it, but I'm going to mention, is that we would need to reify, big word, I'll explain in just a minute, things like 3x. So when a kid looks at 3x, they need to have a lot of things happening simultaneously, sort of built on each other, so that then they can use 3x as an object. So we need things like 3x stands for x plus x plus x, an additive perspective. Ideally, kids would then also connect that to the multiplicative aspect of 3 times something. So that thing plus that thing plus that thing, but that's 3 of those things. But then we also need to not be like in the weeds with that x plus x or that 3 times x, and be able to use 3x as a thing, like it's an object, like we're treating it as this thing is 3x. But I need to be able to dig into it and feel the additive or the multiplicative notion of it. So all that kind of needs to be happening in order for us to do the following. We're not talking about how we're doing that today. You can go listen to a few episodes ago where we did some of that. Where we reflected 3x or negative 3x across the 0. That's in part of that work was happening. Anyway, all right. So moving on. Today, Kim, Join me in a lovely problem string. We are going to use a double open number line. Well, I'm going to use it. You don't have to, but I am. So if I were to say to you, let me just say, we've done the work of the last few weeks. So if you haven't watched the last few weeks, go watch the last few weeks. Here we are. If I said, hey, Kim, I've got this equation, x plus 3y equals 8. We might have a brief conversation about what that could mean. Is it a parabola? Is it an exponential function? Do you have any idea what kind of graph this is?
X plus 3y
Uh-huh.
equals 8. It's
Yep.
a line.
That is correct. That's so with a question mark there. It's a line.
It's a line.
It's a line. Okay.
I was making sure I knew what your question was.
Oh yeah.
Yeah.
Read my mind.
Well, you said it. I was just drawing. You told me what to. You told me, and I started messing, and then I forgot you were still talking.
You forgot you were on a podcast, and we're recording. Okay,
it's going to be a mess today. I can tell you right now, it's a mess.
Well, let's just keep messing. Let's keep messing together.
Okay, I'm with you. It's a line.
So if we have the line x plus 3y equals 8,
yep.
Just for today, just because I'm just sort of curious.
Yep.
To solve for x.
Okay,
so I'm going to use a double open number line, which you might think is totally weird. And I'm going to put, if we know x plus 3y equals 8, we also know that x plus 3y is in the same location as 8.
Yep.
So I've got a double open number line. I've got a tick mark right in the middle. Above it, I've got x plus 3y. Below it, I've got 8.
Yep.
I want to know where x is. If x plus 3y is there, where's x? At least in relation to that 8.
Yeah.
What do you got?
I'm thinking that before I added 3y, x is to the left.
Because then you're going to add 3y, right? To get over there to the right. So I've kind of drawn x to the left of that, and I've drawn a little jump, and I've put 3y above that jump. Okay.
So then below my number line, I'm writing 8 minus 3y, because if I jump back the same amount as I jumped the 3y on the top. So I have now on my number line, x is in the same location as 8 minus 3y.
Nice. And we can kind of use the relationships of location to kind of think about that. Bam. Nicely done. That's it.
We're done? That's the whole string?
With that problem.
I was like, wow, I did great.
Yes, you did. With problem number 1. Number 2. All right. What if the equation of the line is x minus 3y equals 2? Okay. So new number line, whole new problem, not related to the other one in any way. X minus 3y I've now put above the number line where the tick mark is, and 2 is below. And again, I want to solve for x. Where is x?
So before I subtracted 3y, x would have been to the right. So I'm adding 3y, jump of 3y.
Yep.
And so I'm doing that on the bottom as well. So I have 2 plus 3y is in the same location as x.
So over on my equations over there, I could write, so if x minus 3y is 2, then x is going to be equal or in the same location to 2 plus 3y. Nice. Next problem. What about 2x plus y equals 3, but this time I want to know where y is. So if 2x plus y is in the same location as 3, where's just y?
So same thing. I'm thinking about before I added y. So I'm going to subtract y. I'm going to go to the left.
But I want to know where y is.
Oh, I lied. So I'm going to subtract 2x.
Okay.
And that's going to put y to the left of 2x plus y.
Okay.
And then I'm going to subtract 2x from the 3 to kind of slide it to the same location as y. So I have 3 minus 2x.
So y is in the same location as 3 minus 2x. Nice. Okay. Next question. How about 3x minus y equals 9?
Okay.
Tell us what your number line looks like.
3x minus y is on the top, and 9 is at the bottom.
Okay.
What did you say? Solve for y?
Yep. Y again.
Okay. So 3x minus y. You said solve for x for y? Oh, yeah, okay. So,
you can do it.
I can do it. So I want to like have 3x plus y somehow. So before I subtracted y, 3x minus y. Why is this hard for me?
Because it's hard.
So I want 3x to be to the right. I mean, to the right.
Okay.
And then I want 3x plus y to be even further to the right.
3x plus y. 3x. Why do you want 3x to be to the right?
I don't know.
Say that again.
Like, because I was thinking about before I subtracted y, then it would be 3x plus y.
So you're going to the right y, and you're at 3x plus y on the top, and you would be at 9 plus y on the bottom? Okay.
Is that good enough?
Wait, but when you... Hold on a second. Subtracted y. Wouldn't you just be 3x on the top?
Before I subtract... Well, that's what I said at first. If I have... I had 3x, and then would have...
Maybe I wrote it down wrong. Tell me what your number line has.
I have 3x minus y on top and 9 at the bottom. But I want to think about before I subtracted y. So then I would have 3x on the top and 9 plus y on the bottom.
Yeah, I heard you wrong. So that's excellent. I like where you are. Okay. Good. Okay. Sorry. My bad.
And then what am I looking for? I want to know what y is.
Y. Yeah, where's y?
Whew, okay.
You're doing great. You now know where 9 plus y is, but
so
we just want to know y.
I want just y. So I'm going to subtract 9 and I'm going to go back to the left.
Okay.
And I'm going to do subtract 9 to the 3x also. So I have y is 3x minus 9.
So y is now in the same location as 3x minus 9.
Yeah.
Yeah. What do you think? You're done.
Yeah.
Why would we do this string? It seems really random that we would just solve. Well, one of the solution methods to solve a system of equations is to solve for one variable and then use that in the other equation, and then you can find the value of that one variable, and then you can find the value of the other one, and you can find the intersection point. But often, if kids are going to use this substitution method, often one of the things I found with my students that they would mess up is in the solving for one variable. So teachers, you might consider a sequence of tasks where I would do something like we did last week in maybe a couple of contexts. One we just did with the sandwiches and the cookies, where you really give students a sense of what it actually means to even be a system of equations. So go back and listen to that one again if you didn't, but really just like a sense of this system of equations. It is a system if there is, well, I can't quite say it that way. I was going to say if there is an intersection point. You can have a system of equations that there is no solution or that there's an indeterminate solution. But if there is a solution, an intersection point, what does that mean? Oh, and brilliant. I probably should have asked last week when we were talking about the sandwich shop, what does it mean if there wasn't an intersection? And I don't know, Kim, if you want to go there. If I had given you a price of sandwich or a number of sandwiches, number of cookies equals a price, and then a different number of sandwiches, number of cookies equals a different price. And when you graph them, there was no intersection. Do you have any ideas what that would mean?
I mean, it either means I'm in a different sandwich shop or to change the price because they don't have a consistent price.
Yeah. Nice.
Yeah.
So like that, with all of that to develop, when you get to the point where you want kids to get a feel for solving with substitution, I think you could first just give students systems where one of the variables has a coefficient of 1. Well, maybe very first where it's already solved for that variable. They can just take the x. We already have what x equals, plug it in the other one, solve for the system. Then you could give it where the coefficient is 1. So they still have to do a little solving, but it's just the coefficient is 1, kind of like the first couple that I gave you. Well, actually, all of them ones I gave you today, except some of them had one of them had a negative coefficient. And then you would want to do more solving equations work so that they get kind of that idea of dividing if they need to divide out the coefficient before you ever ask them to then do it where they're actually solving the system where things aren't quite as complicated. It's not about making it easy to hard. It's about sort of a systemic progression where kids are thinking about, this makes sense. Now, I have some great problem strings in algebra problem strings and advanced algebra problem strings where the question then is, given this system, how do you want to solve it? And then you give kids free reign, and then you have the conversation. What is it about this system that made you want to use elimination? What is it about this system that made you want to use substitution? What is or use graphing? I'll just finish that and go ahead.
Can I tell you that when my oldest, what grade is this going to be? I don't even know, but I remember him.
This is algebra 1 or algebra 2.
Okay.
Is that what you mean?
So yeah. It might've been algebra 2 because I remember him having, a paper that said, you must solve these with substitution and then you must solve these with elimination. And he and I were both like, wait, what? Why?
Why don't I have choice?
There were some where there were some for sure. Like I'm kind of going back in the recesses of my brain that he was like, but it's so much better to do it the other way. Like, do I have to, what the directions say?
Yeah. Nice point. And I love the fact that he knew that he should have choice.
Yeah.
So teachers right now might be thinking, yeah, but Pam, or Kim, how do we make sure that students can do a method?
Ooh. I know.
All right, go.
I mean, wouldn't want to give them problems for where they would choose, like sometimes you want to give them problems where elimination is like the obvious do that. And then sometimes you do it where the substitution was like the obvious do that. And then
have a conversation about like if kids are stuck, then you're like, ooh, look how nice this would have been. Gives them an opportunity to go, oh yeah, that would have been nice. And your last one, which was give them, I think you were going to say, give them ones where it's a toss up. They could do either. And then they can choose.
Well, and if they're using the same like substitution every time, that might be a sign that like maybe they don't really own or
and then maybe you could do and then maybe you could do a problem string where you really focus on the one that many of your students are struggling with. You could also, this is totally where I thought you were going to go, Kim. We're just planning a live math with Pam. Help me event with our journey group. And one of the things that we're talking about are really cool assessment items. And one of those really cool types of assessments I call ketchup problems. And this would be a fantastic time to do a ketchup problem. Pam, what's a ketchup problem? So picture you're doing your homework and you're eating fries, because yum, fries, and you drop ketchup on your homework. And you get up the next day, you don't realize it. You get up the next day and you're going to turn your homework in and you're like, oh, crumb, I dropped ketchup. And so you're trying to like fill in the blanks where the ketchup, but where the ketchup splattered all over your homework. You got to like write in what you've missed. That's just that's why I call them ketchup problems. But literally you could give students a system and you could solve it. So it's a tweak on a previously saw or showing a strategy that someone else did. So solve the system, and if you want kids to work on elimination, fine. Solve it using elimination, but put blanks, put splotches, and say to the kids, fill in what needs to be here in order for this solution to work. Vice versa, use substitution. Solve it, but put blanks in really nice places that kids have to. That's a way of instead of now. See if Luke got that, or I think it's Luke. If he'd got that assignment, he would have been like, oh, okay, my job here is to fill in the relationships that this student used to solve the problem. It isn't, you must use this strategy to solve this problem, even though you can totally tell there's a better one right now. Right. So it's a lot more agency involved, I think, when we allow students to use what they know to solve problems. But in order to help them not get stuck in a method that we know is not going to be the best one forever, we can then use a ketchup problem to kind of help them follow follow the thinking and fill in sort of the relationships that were used in that thinking. Does that make sense?
Yeah, absolutely.
Yeah, bam. All right.
You know what I'm stuck on? I know you want to end, but
it's all right.
But I'm gonna pause this for a second because I'm stuck on the fact that the fourth problem was harder for me to think about relationally, and I'm looking at the problems that you gave me.
Okay.
And I think it has everything to do with the fact that the y was being subtracted. Like,
absolutely.
That's a different problem. Like,
that's
noteworthy that it's not all the same
difficulty level.
Yeah, it feels like it's related to like problem types for me.
Oh, I like it. I like it. I think that sounds very nice. And it would be a reason why we could do this problem string, and we might not be done. We might need to do another problem string where maybe there's a negative X involved. And then some discussion, a huge discussion about when do you want to use substitution and when do you want to use elimination? Because if there's a lot of coefficients going on, how about if we don't do substitution? Like all that dividing, especially if you end up with fraction coefficients like crazy. Like there might be a better strategy at that point to try at least to consider.
Mm-hmm.
And when is it crazy enough that you just want to throw it in calculator and find the intersection point?
Yeah. Mm-hmm.
And making sure kids know that there are those choices. You know, it's funny, Kim, last, and then we're going to go. Sometimes people will look at the work that we're doing in the elementary school with numeracy, and they'll say, Pam, why are you giving kids all these choices? There's one and only one way. When look, here we are in high school math, when there is like, this is a perfect example of where we in higher math have been demanding kids learn different strategies. We haven't done a very good job of letting them choose often, but we are teaching strategies, maybe trying to teach them as procedures to memorize. And then we can give them choices and build mathematicians. All right, y'all. Thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. Let's keep spreading the word that math is figureoutable.